Out there, beyond the thin blue comfort of Earth's sky, the universe appears calm. Stars rise and set, galaxies drift slowly, light travels for millions or even billions of years without interruption. From a distance, everything looks orderly, measured, almost serene. But every so often, something does not behave the way it should. A signal arrives that lasts less than the blink of an eye, yet carries more energy than entire stars release in that same moment. A galaxy spins as if most of its mass is missing. A region of space pulls everything toward it, even though nothing obvious can be seen there. A patch of ancient light is colder than the rest, for reasons that remain unclear. None of these things are guesses. None are myths. They were measured, repeated, checked again by different instruments, different teams, different generations of astronomers. And each time the data stayed exactly where it was. Modern astronomy is not short on explanations. Equations describe motion with extraordinary precision. Models predict how stars form, how galaxies grow, how space itself expands. Most of the time, those predictions work remarkably well, and then, occasionally, they don't. The strange thing is not that mysteries exist. The strange thing is where they appear. They show up not at the edges of observation, but right in the middle of it. In well-studied galaxies, in familiar physical laws, in regions of space that were expected to be quiet, predictable, and already understood. Why would a planet exist without a star at all, drifting alone through interstellar darkness? How could a black hole grow so massive when the universe itself was still young? Why does time pass at different rates depending on where it is measured, and how can that difference be detected from orbiting clocks? Why does the universe appear to be expanding faster now than it did before? These are not questions asked to provoke fear or wonder for its own sake. They arise naturally from observation, from careful measurement, from instruments doing exactly what they were designed to do. In many cases, the universe does not refuse explanation. It simply delays it. Patterns emerge slowly. Models adjust. What once felt impossible becomes quietly understood. Other times, the explanation remains incomplete, not because it is hidden, but because the available evidence has reached its current limit. There is a particular kind of calm that comes from this, a recognition that the universe does not need to be intuitive to be consistent. That reality does not owe simplicity to those observing it. That understanding is not a destination, but a process. The discoveries explored here are not the loudest or the most dramatic. They are the ones that linger, the ones that made astronomers pause, check their instruments, and look again. They are strange not because they break the rules, but because they reveal how flexible those rules can be. As this journey unfolds, the universe will grow larger, quieter, and occasionally more unsettling. Signals will arrive unexpectedly. Empty regions will stretch farther than intuition allows. Invisible forces will shape visible structures. Time itself will behave differently depending on where it is measured. Nothing here is exaggerated. Nothing is invented. Every phenomenon discussed is real, observed, and part of the universe as it actually is. The only question left is how it all fits together, and in some cases whether it fits at all. For now it is enough to observe, to notice, and to let the strangeness settle gently into view. Most of the time the universe behaves itself. Stars shine for billions of years. Planets follow steady paths. Galaxies rotate, collide, and drift apart in ways that can be measured, predicted, and described with remarkable accuracy. Astronomy, at its heart, is a science built on patience. You observe long enough, you measure carefully enough, and patterns begin to reveal themselves. And then, sometimes, something refuses to sit comfortably inside those patterns, not loudly, not dramatically. Often it arrives quietly, hidden inside a column of data or a strange spike on a graph. At first, it looks like a mistake, a glitch, a sensor hiccup, something to be filtered out and forgotten. Astronomy has learned to be suspicious of surprises. When an observation appears strange, the first assumption is almost always that something went wrong. A cable loose, a calibration error, a cosmic ray hitting a detector at the wrong moment. Instruments are complex and the universe is generous with interference. Caution is not just sensible, it is essential. So the signal is checked again and again. It is compared across instruments built by different teams using different methods, sometimes on opposite sides of the planet or far above it in orbit. The data is shared, scrutinized, questioned by people who would be far more comfortable if it simply went away. Sometimes it does, but sometimes it doesn't. That moment when the measurements remain stubbornly consistent but the explanation lags behind is what astronomers quietly refer to as observational tension. It is not a crisis. It is not a failure. It is a pause, a recognition that reality has delivered an answer before the question was fully formed. This is where the universe begins to feel slightly uncomfortable. Uncomfortable does not mean chaotic. It does not mean physics has broken down. Quite the opposite. The laws still hold. Gravity still behaves, light still travels at the same unwavering speed. What becomes uncomfortable is the gap between expectation and outcome. Something appears too fast, too bright, too early, too empty, or just as unsettling, too quiet. Consider energy. Physics places very firm limits on how much energy an object can release, and how quickly it can do so. Those limits are not arbitrary. They emerge from the structure of space, time, and matter itself. When astronomers talk about objects that emit more energy than they should, they do not mean that the laws have been violated. They mean that the system producing that energy is operating in a way that was not fully anticipated. These moments are not rare. They're woven through the history of astronomy. When the sun's energy output was first calculated in the 19th century, no known chemical process could explain how it could shine for so long. The sun seemed to be producing too much energy for too much time. The data was sound, the explanation was missing. The solution did not arrive until nuclear fusion was understood decades later. The tension dissolved, but the measurements never changed. That pattern repeats. Astronomers do not chase mystery for its own sake. They chase consistency. When independent observations line up too neatly to dismiss, the universe earns the benefit of the doubt. This is why strangeness in astronomy carries a particular weight. These discoveries are not born from speculation. They emerge from systems designed to remove imagination from the process as much as possible. Telescopes do not get excited. Detectors do not exaggerate. They count photons. They measure arrival times. They log motion, brightness, and distance with cold precision. When something looks strange across years of data, across continents, across generations of instruments, it becomes real by persistence alone. There is a quiet humour in this. Astronomers often joke that the universe seems determined to embarrass their best theories, but only gently, and only after those theories have worked beautifully for everything else. Nature is not cruel, it is indifferent. It produces outcomes, not explanations. What makes these uncomfortable observations especially interesting is where they appear. Not at the fringes of knowledge, but right in the middle of it, in galaxies that have been mapped in detail, in stars whose behaviour was thought to be well understood, in regions of space expected to be unremarkable. Sometimes the strangeness lies in abundance. Too many planets drifting without stars, too many massive objects forming too early. Sometimes it lies in absence. Regions of space so empty they seem almost deliberate. Sometimes it lies in silence, where signals were expected but never arrive. In each case, the initial reaction is restraint. No grand claims, no dramatic conclusions, just careful language. Phrases like unexpected, anomalous, or requiring further study. In scientific writing, understatement is often the loudest signal that something truly interesting is happening. And crucially, these moments do not always remain mysterious. In many cases, the tension softens with time. New models are developed, observations improve, what once felt impossible becomes routine. The strange is absorbed, and the universe returns to behaving itself, at least until the next surprise. But not always. There are observations that have lingered for years, even decades, without a fully satisfying explanation. Not because scientists have failed to look hard enough, but because the universe is operating at scales and conditions that stretch intuition. Extreme gravity, extreme density, extreme energy compressed into impossibly small windows of time. These are not cracks in reality, they are seams. Places where different parts of physics meet, sometimes awkwardly. What is remarkable is how rarely this leads to upheaval. The universe does not unravel. It remains stable, consistent, and profoundly reliable. The discomfort exists almost entirely on the human side of the equation. There is something quietly reassuring in that. It suggests that reality is not fragile, that it does not wobble when we fail to understand it immediately. It simply continues on its way, unconcerned with whether its behavior fits neatly inside existing explanations. This chapter is not about one specific object or event. It is about a pattern, a way in which discovery unfolds. Strange data appears, skepticism follows, verification accumulates, and slowly, carefully, astronomy expands its boundaries without drama. In the moments ahead, that pattern will repeat. Signals will arrive that seem impossibly brief. Objects will release astonishing amounts of energy in ways that defy first impressions. Measurements will suggest that something essential is missing, or that something unexpected is present. None of it requires belief, only attention. The universe is not trying to confuse anyone. It is simply revealing itself at scales where common sense becomes an unreliable guide, and when observation becomes uncomfortable, that discomfort is often a sign that something important has just come into view. The next time it happens, it will arrive quietly, in a fraction of a second, logged automatically, dismissed briefly, and then, slowly, accepted as real. That is usually how the strangest discoveries begin. For most of the history of astronomy, the universe communicated slowly. Light drifted in over years, decades, centuries. Stars brightened and dimmed gently. Galaxies evolved at a pace so gradual it could barely be noticed within a human lifetime. Even violent events like supernovae unfolded over days or weeks when viewed from afar. So when something arrived that lasted only a few thousandths of a second, the first assumption was not discovery. It was error. The earliest fast radio bursts were found almost by accident, buried inside vast archives of radio data. Radio telescopes listened constantly, recording enormous volumes of information from across the sky. Most of it is noise, some of it comes from familiar sources, and some of it, inevitably, comes from Earth itself. Satellites, aircraft, microwaves warming someone's lunch at the wrong moment. When a sharp, bright spike appeared, lasting only a millisecond, it looked exactly like interference. Too brief, too sudden, too inconvenient. So it was ignored. That first signal was recorded in the early 2000s, but it was not recognized for years. Only later, when astronomers began combing through old data with new techniques, did it resurface. The burst had all the fingerprints of something extraordinary. Its radio waves had been stretched by their journey through intergalactic space, a clear sign that it had travelled vast distances before reaching Earth. This was not local noise. It was not even coming from within the Milky Way. It was arriving from another galaxy entirely. Even then, caution ruled. One detection could still be a fluke, something unusual but not necessarily astrophysical. The universe does not reveal itself with a single data point. What changed everything was repetition. Over time, more of these flashes were found. Different telescopes, different parts of the sky, different teams working independently. The signals varied slightly, but the core features remained the same. Extremely short duration, immense brightness, a dispersion pattern that betrayed a long journey through sparse intergalactic material. By the time dozens had been catalogued, denial was no longer an option. Fast radio bursts were real, and they were deeply strange. To appreciate just how strange, it helps to consider the timescale involved. A millisecond is 1,000th of a second. In that time, light itself travels only a few hundred kilometers. Any object producing such a brief pulse cannot be very large, at least not in the direction the signal is coming from. Physics places strict limits here. The size of a source and the speed of a light impose a natural boundary. And yet, despite this tiny window, the energy carried by a fast radio burst can rival what the sun emits over days or even longer. This is where discomfort sets in. Energy is not mysterious. It is carefully accounted for in physics. If something emits an enormous amount of energy in a very short time, that energy must come from somewhere. The problem with fast radio bursts is not that they violate any laws. It is that they operate right at the edge of what those laws comfortably allow. They are, quite literally, objects that emit more energy than they seem like they should. At first, astronomers wondered whether all fast radio bursts were the same phenomenon. One cause, one explanation. That idea did not last long. Some bursts were never seen again. They appeared once, flared brilliantly, and vanished forever. Others repeated. Not regularly, not predictably, but often enough to be unmistakable. The same patch of sky would flash again days, weeks, or months later. That single distinction changed the conversation entirely. Repeating bursts could be studied in detail. Their locations could be narrowed down. Their host galaxies could be identified. Their environments could be examined. Non-repeating bursts, by contrast, remained elusive. They offered only a single moment of information before slipping back into silence. This strongly suggested that fast radio bursts were not one thing, but a category. A family of events that shared outward behaviour while hiding very different inner mechanisms. This is a familiar pattern in astronomy. For a long time, gamma-ray bursts were also treated as a single mystery, until they were eventually separated into different classes with different origins. Fast radio bursts seem to be following a similar path. As more data accumulated, another important clue emerged. The repeating bursts tended to come from energetic environments, regions of active star formation, places where massive stars are born, live briefly and die violently. That narrowed the field considerably. Slowly a suspect emerged, not as a guess, but as a result of elimination. Neutron stars. More specifically, a rare and extreme variety of neutron star capable of producing enormous bursts of energy in short, violent outbursts. Objects already known to distort space around them, crack their own crusts, and unleash radiation powerful enough to be detected across galaxies. When one of these objects, located within our own galaxy, produced a radio burst that closely resembled those arriving from distant galaxies, the connection became impossible to ignore. At least some fast radio bursts were coming from these compact stellar remnants. This was not the end of the mystery. It was the beginning of clarity. Because even with a known source, questions remain. Why do some bursts repeat while others do not? Why do their energies vary so widely? Why do some environments seem to produce them more readily than others? And perhaps most intriguingly, Are there other sources still waiting to be identified? Astronomy is comfortable with this kind of uncertainty. It is a measured uncertainty bounded by observation. Each fast radio burst adds another data point, another constraint, another small step toward understanding. There is also something humbling about the way these signals are detected. They do not announce themselves. They arrive without warning, vanish almost immediately, and leave behind only a trace in stored data. Miss the moment, and it is gone forever. This has forced astronomy to change how it listens. New instruments are designed to watch wide swathes of the sky at once. Automated systems flag unusual signals in real time. The universe, it turns out, is not just something to be observed patiently. Sometimes it has to be caught in the act. There is a quiet irony here. Some of the most energetic events ever observed announce themselves almost apologetically, in whispers rather than shouts. A brief flicker in radio waves, a tiny spike on a screen. Enough to be missed if no one is paying attention. Fast radio bursts remind us that the universe is capable of compressing astonishing amounts of activity into astonishingly small windows of time. That violence does not always look dramatic from a distance, and that energy, when confined and released under extreme conditions, can appear almost magical, even when it obeys every known rule. They also serve as a gentle warning. If something this extreme can hide in plain sight for years, there may be other signals passing through the cosmos right now, unnoticed, unrecognized, and waiting patiently inside data that has not yet been fully explored. For now, these brief flashes stand as some of the most unexpected discoveries of modern astronomy. Not because they are loud or threatening, but because they challenge assumptions about how quickly and how intensely the universe can act. They arrive in less time than it takes to blink, and yet, in that moment, they manage to tell a much longer story. Some stars end their lives quietly. They swell, shed their outer layers, and fade into dense, cooling remnants that drift through space almost unnoticed. Others, however, refuse to go gently. They collapse inward with such force that the very structure of matter is pushed to its limit. What remains after such a collapse is not a star in the familiar sense. It is something far smaller, far denser, and far stranger. A neutron star begins its existence when a massive star exhausts its fuel and can no longer support itself against gravity. The core collapses in on itself so violently that protons and electrons are forced together, forming neutrons. The result is an object with the mass of the Sun packed into a sphere roughly the size of a city. This is not an exaggeration. A single teaspoon of neutron star material would outweigh mountains. At these densities, atomic structure barely survives. Matter is squeezed into configurations that cannot exist anywhere else in the universe, at least not for long. Despite this, neutron stars are remarkably stable. They spin with extraordinary regularity. Some rotate hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. These objects, known as pulsars, were once so unexpected that their signals briefly raised eyebrows for entirely the wrong reasons. But even among neutron stars there are extremes. A small fraction possess magnetic fields so intense that familiar language begins to fail. These fields are not just strong, they are overwhelming, trillions of times stronger than Earth's magnetic field, strong enough to alter the shape of atoms, strong enough to affect the vacuum of space itself. These objects are known as magnetars. The name is dramatic, but the physics behind it is precise. Magnetars are neutron stars whose magnetic energy dominates their behavior. While gravity still holds them together, magnetism dictates almost everything else. This creates tension. Not observational tension this time, but physical tension. The outer layers of a neutron star are rigid beyond anything found on Earth. Often described as a crust, this layer is only a few kilometers thick, but it is incredibly strong. Under normal circumstances, it can withstand enormous stress. A magnetar does not behave normally. As its magnetic field evolves and rearranges itself, stress builds up inside the star. The crust resists for as long as it can, holding back forces that defy intuition, and then, occasionally, it fails. When it does, the result is a starquake. These events are not subtle. The crust fractures, releasing vast amounts of energy in an instant. Gamma rays and X-rays flood outward. In some cases, the burst is so powerful that it can briefly affect Earth's upper atmosphere from across the galaxy. One such event, observed in the early 2000s, released more energy in a fraction of a second than the Sun emits over hundreds of thousands of years. Detectors designed to study distant cosmic explosions were momentarily overwhelmed. Some instruments even mistook the burst for a fault, saturating before anyone could react. Once again, the first instinct was disbelief. But the data held. Independent satellites recorded the same spike. The timing matched, the direction aligned. The universe had delivered another uncomfortable measurement. These giant flares are among the most energetic events known that do not involve black holes, and yet they come from objects only tens of kilometers across. This is another example of something that emits more energy than it seems like it should given its size. The explanation lies in stored magnetic energy. Magnetars act like tightly wound springs made of magnetic field lines. When those lines snap into a new configuration, energy is released with astonishing efficiency. The effects are not limited to radiation alone. The intense magnetic field of a magnetar can distort the space around it. It can influence the motion of charged particles at vast distances. It can even alter how light propagates nearby. Matter, under these conditions, behaves in unfamiliar ways. Electrons are forced into elongated orbits. Atomic bonds stretch and warp. The usual rules of chemistry become almost irrelevant. This is not because physics fails, but because it enters a regime that is rarely encountered. Studying magnetars allows scientists to test theories of matter under extreme pressure and magnetism, conditions that cannot be replicated in any laboratory on Earth. In this sense, magnetars are not just exotic objects. They are natural experiments conducted by the universe itself. Their relevance extends beyond their own dramatic behavior. When astronomers began linking some fast radio bursts to magnetars, it provided a crucial anchor point. Here was a known object, governed by understood physics, capable of producing bursts of energy on the right timescales, with the right intensity. A particularly telling moment came when a magnetar within the Milky Way produced a radio burst that closely resembled those arriving from distant galaxies. It was not identical, nothing ever is. But it was close enough to establish a connection that could not be ignored. This did not mean that all fast radio bursts came from magnetars. It meant that at least some of them did. And that distinction matters. It reinforces a pattern that appears again and again in astronomy. The universe rarely relies on a single mechanism to produce a given phenomenon. Similar signals can arise from different sources, under different conditions, across different environments. Magnetars represent one extreme pathway. Other pathways may exist. The universe is rarely economical in its creativity. What makes magnetars especially compelling is that they feel both alien and grounded at the same time. Their behavior is extraordinary, but it follows from well-defined principles: gravity, quantum mechanics, electromagnetism. Push those principles far enough, and magnetars emerge naturally. There is also something quietly reassuring about their rarity. Magnetars are uncommon. Only a few dozen are known within the Milky Way. They do not dominate the galaxy. They punctuate it. When one becomes active, it briefly reminds astronomers that even well-categorized objects can surprise them. That a star, long after its death, can still store enough energy to announce itself across vast distances. Despite their violence, magnetars are not chaotic. Their outbursts are sporadic, separated by long periods of relative calm. Most of the time, they simply spin, cool, and slowly evolve. Violence in the universe is often episodic. There is a gentle irony here. Some of the most extreme conditions known exist in objects that are, on cosmic scales, tiny. The universe does not require vast size to produce dramatic effects. Compression, confinement, and time are often enough. Magnetars teach an important lesson. Enormous energy does not always come from enormous objects. Sometimes it comes from small things pushed to extraordinary limits. As understanding improves, the initial shock fades. What once felt impossible becomes explainable. What once felt magical becomes measurable. The discomfort softens, not because the universe has changed, but because perspective has. Yet magnetars still retain an edge. They occupy a boundary where matter, energy, and space interact in unfamiliar ways. They remind scientists that extreme does not mean rare enough to ignore. And they serve as a bridge, a link between fleeting signals that last less than a blink and the physical engines capable of producing them. From here the universe grows quieter again. Not calmer necessarily, but less violent. Attention shifts away from compact remnants that crack under their own internal strain, toward objects that drift silently through space, emitting almost nothing at all. In a universe capable of both, silence can be just as surprising as noise. Most planets, at least in the familiar picture, are defined by what they orbit. A star sits at the centre, shining steadily, while planets trace predictable paths around it. Warmth, light, seasons, and even the concept of a year all depend on that central presence. Remove the star, and the picture seems to fall apart. And yet the universe does not appear to mind. Scattered through interstellar space are planets with no sun at all, no dawns, no sunsets, no steady source of light or heat. These are rogue planets, worlds that drift freely through the galaxy, bound only to the gravity they carry with them. For a long time, such objects were purely theoretical. Planet formation models suggested they should exist, but there was no obvious way to find them. A planet without a star is, by definition, dark. It does not shine. It reflects nothing. Against the vast backdrop of space, it is effectively invisible. And yet they were found anyway. The key was not to look for light, but for gravity. Gravitational microlensing relies on a subtle but powerful idea drawn directly from general relativity. When a massive object passes in front of a distant background star, its gravity bends the star's light slightly, acting like a lens. The background star appears to brighten for a short time, not because it has changed, but because its light has been focused. Most microlensing events are caused by stars. Their mass creates a characteristic brightening that lasts days or weeks, but occasionally astronomers notice something different, a brief brightening, sometimes lasting only hours, too short to be caused by a star. The only explanation was something much smaller, a planet. Crucially, these events occurred in places where no host star could be found, no companion, no nearby source of light. The planet was alone. This was the first direct evidence that rogue planets exist. From there, the numbers began to grow. Large surveys, monitoring millions of stars over long periods, detected more and more of these fleeting lensing events. Each one was brief, each one was rare, but taken together they painted a surprising picture. There appeared to be a great many of them. In fact, statistical analyses suggested that rogue planets might be as common as stars in the Milky Way, or possibly even more numerous. This was not a claim made lightly. It emerged from careful modelling, accounting for detection bias, survey sensitivity, and the fact that many events would inevitably be missed. The conclusion was not that every star ejects multiple planets. It was that planetary systems, especially in their early stages, can be far more chaotic than once imagined. When planets form, they do not settle immediately into neat, stable arrangements. Young planetary systems are crowded places. Massive planets migrate inward and outward. Smaller worlds are tugged, scattered, and sometimes flung away entirely. Gravity is a poor negotiator. If a planet strays too close to a larger neighbour, or if a system undergoes a period of instability, the result can be ejection. The planet is accelerated to escape velocity and cast out into interstellar space, never to return. This process does not require catastrophe. It does not require an exploding star or a passing interloper. It can happen quietly, as a natural outcome of orbital dynamics. Over billions of years, the galaxy has had plenty of time to produce a population of wanderers. What makes rogue planets especially intriguing is how little is known about their physical properties. Microlensing reveals mass, but not composition. A rogue planet could be a gas giant like Jupiter, or a rocky world like Earth. It could retain a thick atmosphere, or lose it entirely. It could even possess internal heat from radioactive decay, or residual formation energy. Some scientists have speculated, carefully and without sensationalism, that subsurface oceans could persist on certain rogue planets, kept warm by internal heat and insulated by thick ice layers. This is not a claim of life. It is an acknowledgement that habitability, like many concepts in astronomy, may be broader than once assumed. But it is important to remain grounded. What is directly observed is simple: a temporary brightening of a background star, a gravitational signature, a mass estimate. Everything beyond that is inference, guided by physics but limited by data. There is a certain elegance to this restraint. Rogue planets are not made mysterious by embellishment. They are mysterious because they exist at all, drifting unseen through a galaxy filled with light. They also challenge how planets are defined. Traditionally, a planet was understood as something that orbits a star. Rogue planets break that definition cleanly. They are planets by mass and composition, not by relationship. In this way, they resemble magnetars and fast radio bursts, not in behaviour, but in what they reveal. The universe is comfortable producing objects that fit the rules locally, while violating expectations globally. There's also something quietly humbling about their isolation. These worlds travel through the dark between stars, passing unseen by almost everything. They may drift for millions or billions of years without interacting with another object. No orbit, no anchor, just motion. And yet they are not anomalies. They are part of the natural outcome of planet formation. The galaxy, it seems, is littered with the byproducts of gravitational negotiation. From a distance, this might feel unsettling. Planets are often associated with stability, cycles, and predictability. Rogue planets suggest a universe that is less tidy, more willing to scatter its creations. But there is another way to see it. Rogue planets represent freedom. They are proof that not everything must be bound to a luminous centre to exist. That complexity can persist even when connection is severed. They also remind astronomers that absence of light does not mean absence of substance. Much of the universe operates in shadow, detectable only through indirect effects. In that sense, rogue planets serve as a quiet bridge between the violent extremes of compact stars and the vast structures of galaxies. They occupy a middle ground, solid, silent, elusive. As detection techniques improve, more will be found. Some may be closer than expected. Some may pass quietly through the outskirts of stellar neighbourhoods, unnoticed except for a brief gravitational whisper. And while individual rogue planets remain difficult to study, their collective presence is unmistakable. They are numerous enough to matter, numerous enough to reshape how planetary populations are counted. The universe once again reveals that it's not obligated to conform to familiar arrangements. Stars do not always keep their planets. Light does not always accompany mass. Order does not always persist. From solitary worlds drifting through darkness, attention naturally shifts outward, beyond individual planets, beyond stars, toward regions of space where not just light, but matter itself becomes scarce. Places where even galaxies begin to thin out. Places where emptiness takes on a structure of its own. Space is often imagined as empty by default. Between stars, between galaxies, between everything that shines, there seems to be nothing at all. Early astronomy leaned into that idea quite comfortably. Galaxies were treated like isolated islands scattered randomly through an otherwise featureless ocean. That picture did not survive careful mapping. As telescopes improved and surveys grew larger, astronomers began to notice patterns that were impossible to ignore. Galaxies were not sprinkled evenly through space. They clustered. They aligned. They traced long filaments and sheets, forming an intricate network now known as the cosmic web. To see this structure clearly required a very specific kind of measurement. Galaxy redshift surveys do more than simply record where galaxies appear on the sky. They also measure how fast those galaxies are moving away due to the expansion of the universe. That motion stretches the light they emit, shifting it toward the longer wavelengths. The amount of stretching reveals distance. With enough data points, a three-dimensional map emerges. And when those maps were first assembled, something unexpected stood out. Huge regions contained almost nothing at all. These were not small gaps. They were not statistical flukes. They were vast volumes of space, spanning tens or even hundreds of millions of light years, with far fewer galaxies than anyone had predicted. These regions came to be known as cosmic voids. The name sounds dramatic, but the reality is subtle. A void is not completely empty. There may be a few faint galaxies scattered within it, thin wisps of gas, dark matter drifting quietly through. But compared to the dense filaments and clusters surrounding them, voids are profoundly underpopulated. They are the negative space of the universe. What made this discovery so unsettling at first was not just the size of these voids, but their regularity. They were not randomly placed. They fit neatly into the cosmic web, surrounded by walls and filaments of galaxies, like bubbles pressed together in a foam. Emptiness, it turned out, had structure. This forced a shift in perspective. Instead of asking where galaxies are, astronomers began asking where galaxies are not, and why. The absence of matter became just as informative as its presence. One void in particular stood out. Located in the direction of the constellation Boötes, this region appeared almost alarmingly empty. Early surveys found only a handful of galaxies where hundreds might normally be expected. Its diameter stretched for hundreds of millions of light years, making it one of the largest known voids in the observable universe. This became known as the Boötes void. When it was first identified in the late 1970s, it challenged intuition in a very direct way. How could such a large region remain so empty in a universe that had 13 billion years to mix and evolve? Why had matter not flowed in to fill the gap? At first, there was skepticism. Perhaps the galaxies were simply too faint to detect. Perhaps dust obscured the view. Perhaps the surveys were incomplete. As observations improved, those explanations fell away. Deeper surveys confirmed the emptiness. Different wavelengths told the same story. The Boötes void was real, and it was not alone. Other voids of comparable scale were found elsewhere, forming a repeating pattern across the cosmos. Rather than being anomalies, voids were a natural outcome of structure formation. To understand why, it helps to think back to the early universe. Matter was not distributed perfectly evenly. Tiny fluctuations in density existed from the beginning. Over time, gravity amplified those differences. Slightly denser regions pulled in more matter, growing into filaments and clusters. Less dense regions lost material, becoming emptier as matter flowed away. The result was a universe that organized itself into contrast. Dense regions became denser, empty regions became emptier. In this sense, voids are not failures of structure. They are a direct consequence of it. What is particularly fascinating is that voids continue to influence the universe around them. Galaxies on their edges tend to move outward, pushed away as the void expands along with the universe. The boundaries between voids and filaments are dynamic, shaped by gravity over billions of years. Voids are not static holes, they evolve. They also offer unique laboratories for studying cosmology. Because they contain relatively little matter, physical processes within voids are simpler. Galaxies inside them experience fewer interactions. Their evolution is less disturbed. This allows astronomers to isolate certain effects that are harder to see in crowded environments. In a way, voids provide quiet control experiments on a cosmic scale. There's also something deeply counterintuitive about their scale. When standing on Earth, emptiness feels small, a gap between objects, a pause. In the universe, emptiness can span distances that defy imagination. The Boötes void alone is large enough to swallow tens of thousands of galaxies like the Milky Way, with room to spare, and yet it does not feel dramatic when observed. There is no sharp boundary, no sudden drop, just a gradual thinning until the cosmic web fades into near-nothingness. This subtlety is part of what makes voids so compelling. They do not announce themselves, they reveal their presence only through careful absence. There is a gentle humour in this. Some of the largest structures ever identified are defined not by what they contain, but by what they lack. The universe, once again, resists simple categorization. Importantly, voids do not undermine existing theories, they reinforce them. Modern simulations of cosmic evolution naturally produce voids of varying sizes. The Boötes void sits at the larger end of that distribution, but it does not break it. It simply reminds astronomers that randomness and scale can occasionally align to produce something that feels extraordinary. And feeling extraordinary is not the same as being inexplicable. As surveys have grown more precise, the cosmic web has come into sharper focus. Filaments glow with galaxies, clusters blaze with activity, and between them, voids stretch quietly, holding their shape across immense spans of space and time. Together they form a universe that is neither chaotic nor uniform, but delicately structured. From solitary rogue planets drifting through darkness, attention has now widened to emptiness itself. Not the emptiness between stars, but the emptiness between entire galactic neighborhoods. It is a shift in scale that can feel disorienting. And yet, this is still only the present-day universe, a snapshot of structure billions of years after the beginning. Imprinted beneath it all is an even older record, carried not by galaxies, but by light itself. Light that has been travelling since the universe was young. Light that still carries faint irregularities from that earliest time. One of those irregularities, like the voids before it, stands out not because it is bright, but because it is slightly colder than expected. And like the largest empty places ever mapped, it asks a quiet question about how uniform the universe ever truly was. Long before the first stars ignited, before galaxies gathered into filaments and voids, the universe was filled with light. Not the kind of light that comes from stars or glowing gas, but a smooth, pervasive glow that existed everywhere at once. In the earliest moments after the universe began expanding, space was hot, dense, and opaque. Light could not travel freely. Photons scattered constantly, trapped in a thick fog of charged particles. Then, as the universe expanded and cooled, a quiet transition took place. Electrons combined with atomic nuclei. Space became transparent. Light was finally able to move without interruption. That light has been travelling ever since. Today it reaches Earth from every direction, faint and stretched by billions of years of expansion. It arrives not as visible light, but as microwave radiation, cooled to just a few degrees above absolute zero. This is known as the cosmic microwave background, and it is the oldest light that can ever be observed. In many ways, it is a photograph of the universe as it was when it was only a few 100,000 years old. At first glance, that photograph looks remarkably uniform. The temperature of this background radiation is almost the same everywhere. Variations are tiny, amounting to differences of a few parts in 100,000. This smoothness is one of the great successes of modern cosmology. It confirms that the early universe was extraordinarily even, with only slight ripples in density. Those ripples mattered. They became the seeds from which all later structure grew. Galaxies, clusters, filaments, voids. Everything large and familiar today traces its origin back to those minute fluctuations, frozen into the cosmic microwave background. So astronomers study it with extreme care. Space missions and ground-based observatories have mapped this ancient light in exquisite detail, refining measurements over decades. Each improvement sharpened the picture, revealing subtle patterns and correlations that help test theories of cosmic evolution. And within those maps, one feature stood out, not because it was bright, but because it was colder than expected. This region, now known simply as the cold spot, appears as a patch of sky where the cosmic microwave background temperature dips below the surrounding average by a noticeable amount. On its own, that might not seem remarkable. Small temperature variations are expected. What made this different was its size and depth. The cold spot spans a region of sky far larger than most fluctuations, and statistically, it sits at the extreme end of what standard models predict. Not impossible, but unlikely enough to invite attention. As with many discoveries in astronomy, the first response was skepticism. Perhaps it was an artifact of the instrument, a calibration issue, a foreground effect caused by dust or gas within the Milky Way. After all, the galaxy lies between Earth and much of the cosmic background, and separating local effects from ancient signals is a delicate task. So the checks began. Independent missions observed the same region, different instruments, operating at different frequencies, all saw the same feature. Corrections for foreground contamination were applied and reapplied. The cold spot remained. It was real. That did not mean it was mysterious in the dramatic sense, but it did mean it required careful explanation. To understand why it stood out, it helps to consider probability. The cosmic microwave background is not perfectly uniform, but its fluctuations follow well-understood statistical patterns. Most hot and cold spots fall comfortably within expected ranges. Very large deviations are rare, but not forbidden. The cold spot sits in that grey area. It is unusual enough that it cannot be ignored, but not so extreme that it demands exotic explanations by default. In scientific terms, it represents a mild but persistent tension. Several possible explanations have been explored. One involves large-scale structure closer to us. If light from the cosmic microwave background passes through a vast region of relatively empty space on its way to Earth, it can lose a small amount of energy due to the expansion of that region. This effect, predicted by general relativity, can imprint a slightly cooler patch on the background. In this scenario, the cold spot would not be a feature of the early universe at all, but a consequence of more recent cosmic geography. Another possibility is that it truly is a rare statistical fluctuation. Given enough sky, improbable patterns will occasionally appear. The universe offers only one realization of itself after all. There is no ensemble of universes to average over. A third class of ideas looks to the earliest moments of cosmic history, where small deviations in inflationary processes could leave behind subtle imprints. These ideas are treated cautiously because they are difficult to test directly. What matters most is not which explanation ultimately prevails, but how the process unfolds. At every step, astronomers resist the urge to jump to conclusions. Each hypothesis is evaluated against data. New observations are folded in. Models are refined. Some ideas are set aside quietly when they fail to match reality. The cold spot has now been studied for decades, and while its existence is no longer in doubt, its precise origin remains open to interpretation. What is not debated is the nature of the cosmic microwave background itself. Its temperature, spectrum, and overall uniformity are among the most precisely measured quantities in all of science. The cold spot does not undermine that foundation. It sits atop it. There is something deeply instructive about this. The universe allows for oddities without losing coherence. A single unusual feature does not unravel the entire picture. Instead, it becomes a place to probe assumptions, refine statistics, and test how robust theories really are. In a way, the cold spot is a reminder that even the earliest snapshot of the universe carries imperfections. Not flaws, but variations. The cosmos was never perfectly smooth. It was always just uneven enough to become interesting. There is also a quiet poetic element to it. The oldest light in existence, travelling for nearly the entire age of the universe, still carries faint fingerprints of its beginnings. Tiny temperature differences, frozen in time, telling a story that began long before stars or planets existed. And among those fingerprints, one patch stands out as slightly colder, slightly quieter, slightly more reluctant to blend in. That reluctance is not a threat to understanding, it is an invitation to look more closely. As data improves, explanations may converge, or the cold spot may remain a statistical outlier, a reminder that probability allows for rare events. Either outcome is scientifically satisfying. What matters is clarity about what is known and what is not. The cosmic microwave background is real. Its fluctuations are real. The cold spot is real. The debate lies not in measurement, but in interpretation. This distinction is essential. It separates genuine mystery from imagined one. It keeps astronomy grounded, and it also provides a natural bridge. Because the same ancient ripples that seeded galaxies also set the stage for the distribution of matter today. From early temperature differences emerged dense regions and empty ones. From those, galaxies formed. And in some cases, those galaxies now appear to be missing something fundamental. As attention shifts away from the universe's first light and toward its present-day structures, the question is no longer about temperature, but about mass, about what is there, and about what seems, puzzlingly, to be absent. When astronomers talk about galaxies, they're rarely talking about what can be seen. Stars are the most obvious feature. They shine, they cluster, they trace graceful spirals and glowing ellipses across the sky. Gas clouds glow faintly. Dust absorbs and scatters light. All of this can be photographed, catalogued, and admired. And yet, for nearly a century now, astronomers have known that most of a galaxy's mass does not shine at all. This conclusion did not come from theory first. It came from motion. When astronomers began measuring how fast stars orbit within galaxies, something felt off. According to classical expectations, stars farther from the centre should move more slowly, much like planets in the outer solar system take longer to complete an orbit. Gravity weakens with distance. That relationship is reliable. Except in galaxies, it did not happen. Stars far from the galactic centre were moving too fast. So fast, in fact, that without additional mass holding them in place, they should have escaped entirely. The visible matter simply was not enough to explain what was observed. There were only two possibilities. Either gravity behaved differently on large scales, or there was more mass than could be seen. The second explanation proved far more robust. Dark matter entered astronomy not as a mysterious substance, but as a bookkeeping necessity. Something unseen was contributing gravity, something abundant, diffuse, and persistent. Over time, evidence accumulated: galaxy rotation curves, gravitational lensing, the growth of large-scale structure. Independently, each pointed to the same conclusion. Galaxies are embedded in massive halos of invisible matter that outweigh their stars by a large margin. Dark matter became a quiet foundation beneath nearly every model of cosmic structure, which is why a certain class of galaxies cause such discomfort. These galaxies appeared to lack dark matter entirely, or at least to contain far less of it than expected. The first reports were met with caution, bordering on disbelief. Given how central dark matter is to galaxy formation, a galaxy without it seemed almost contradictory. How could such an object even exist? The answer began, as it often does, with careful measurement. Galaxy mass is inferred by observing how stars move. By measuring the velocities of stars orbiting within a galaxy, astronomers can calculate how much gravity is required to keep those stars bound. The faster the stars move, the more mass must be present. In most galaxies, the inferred mass far exceeds what can be accounted for by visible matter alone. Dark matter fills the gap. But in a handful of galaxies, the numbers lined up differently. Stars moved as if the mass present was almost entirely visible. Rotation curves fell off where expected. Velocity dispersions remained modest. The telltale signature of a dominant dark matter halo was missing. This was not subtle. The difference was large enough to stand out clearly against measurement uncertainty. Naturally, alternative explanations were explored. Distances were rechecked. After all, an error in distance affects mass estimates significantly. Stellar populations were reanalyzed. Gas content was accounted for carefully. Observations were repeated using different instruments and methods. The results held. These galaxies genuinely appeared to be deficient in dark matter. It is important to be precise here. These are not galaxies with zero dark matter. That would be an extraordinary claim. Instead, they are galaxies whose dark matter content is dramatically lower than typical for their size and type. They are exceptions, not replacements. This distinction matters. Rather than overturning dark matter theory, these galaxies refine it. They demonstrate that dark matter distribution is not uniform or inevitable. Under certain conditions, it can be stripped away or prevented from accumulating. Several mechanisms have been proposed. One involves tidal interactions. When galaxies pass close to much larger neighbours, gravitational forces can pull material away. Because dark matter halos are more extended than stellar components, they are especially vulnerable to stripping. A galaxy can lose much of its dark matter while retaining its stars. Another possibility involves formation history. Some galaxies may form in environments where dark matter is distributed unusually, leading to systems that are star-rich but halo-poor. There is also the role of feedback. Intense periods of star formation can drive gas outward, altering the gravitational potential and affecting how dark matter settles. Each explanation fits within known physics. None require abandoning established models. What makes these galaxies interesting is not that they defy dark matter, but that they highlight its behavior. They reveal that dark matter is not glued to galaxies in a simple way. It responds to environment, history, and interaction. There is a quiet irony here. Dark matter, once introduced to explain missing mass, now itself becomes something that can be missing. The universe, it seems, enjoys symmetry. These discoveries also serve as stress tests. By studying galaxies at the edges of expectation, astronomers can probe how flexible their models truly are. If a theory only works in average cases, it is incomplete. If it can accommodate extremes without breaking, it gains credibility. So far, dark matter has passed this test. The existence of dark matter-poor galaxies does not undermine the overwhelming evidence for dark matter on cosmic scales. Instead, it sharpens questions about how it behaves locally. There is also something quietly humbling about these objects. They remind us that even well-established ideas must remain open to nuance. The universe rarely obeys averages exactly. It produces outliers, and those outliers often teach the most. From a distance, a galaxy without much dark matter looks ordinary. Stars still orbit, light still shines. Nothing dramatic announces the absence. Only careful measurement reveals the difference. Once again, the strange hides in plain sight. These galaxies also provide a useful comparison point. By studying systems with and without dominant dark matter halos, astronomers can isolate the effects of gravity, feedback, and environment more cleanly. Differences that were once tangled become clearer. In this way, absence becomes informative. It is worth noting that these galaxies are rare. Most galaxies remain firmly dark matter dominated. The cosmic web still relies on invisible mass to hold its structure together. Clusters still bend light. Large-scale simulations still require dark matter to match observation. The universe is not walking back its earlier clues, it is adding footnotes, and footnotes, in science, are often where the most interesting clarifications live. As measurements grow more precise and surveys expand, more of these unusual galaxies may be found. Or they may remain rare curiosities, valuable precisely because of their scarcity. Either way, they reinforce a broader theme. Astronomy advances not by finding one perfect rule, but by understanding the full range of outcomes that reality allows. From here, attention shifts once again. If some galaxies appear to be missing mass they were expected to have, others seem to possess too much mass far earlier than they should. Objects so heavy, so luminous, that their very existence challenges timelines rather than distributions. The puzzle of absence gives way to a puzzle of excess, and once again, gravity waits at the centre of the story. Some of the brightest objects in the universe are not stars at all. They are the glowing hearts of distant galaxies, shining so intensely that they can outshine every star around them combined. From across billions of light years, they announce their presence with unwavering brilliance, cutting through cosmic distance like beacons. These objects are known as quasars. At first glance, quasars appear deceptively simple, a single point of light, sharp, bright, unremarkable in shape. Early observations even mistook them for nearby stars until their true distances were measured. When astronomers realized just how far away these points of light were, the implications became impossible to ignore. Something extraordinarily powerful was at work. Quasars are now understood to be powered by supermassive black holes. Not black holes in the sense of invisible voids quietly consuming their surroundings, but dynamic engines surrounded by swirling disks of gas and dust. As material spirals inward, it heats up, releasing vast amounts of energy before crossing the point of no return. This process is remarkably efficient. A black hole does not need to consume much material to shine brightly. The energy comes not from the matter disappearing, but from it being accelerated, compressed, and heated as it falls inward. From this glow, astronomers can infer the mass of the black hole at the centre. The brightness places limits on how much material can be falling in. The motion of nearby gas reveals the strength of the gravitational pull. Over time, these measurements have become increasingly precise. And that is where the discomfort began. Some quasars were found at extreme distances, meaning their light began its journey when the universe was very young. In cosmic terms, these objects existed only a few 100 million years after the first stars formed, yet the black holes powering them were already enormous. In some cases, their masses reached billions of times that of the Sun. This posed a simple but unsettling question. How did they grow so fast? Black holes are not born large. They typically begin as the remnants of massive stars, with masses a few times that of the Sun. From there, growth is gradual. Matter must fall in. Mergers must occur. Even under ideal conditions, there are limits to how quickly this can happen. There is a maximum rate at which a black hole can accrete material without blowing that material away with radiation. This limit is well understood. It sets a natural speed limit on growth. Given that limit, building a billion solar mass black hole should take a very long time, and yet the universe seemed to have done it remarkably quickly. At first, astronomers wondered whether the mass estimates were wrong. Distances were rechecked, models were refined, independent observations confirmed the results. The quasars were real, their luminosity was real, their black holes were massive. The timeline was the problem. Once again, this was not a case of physics breaking. It was a case of physics being pushed into an unfamiliar corner. To resolve the tension, researchers began exploring alternative growth pathways. One idea was that some black holes did not start small. Instead of forming from stellar remnants, they might have formed directly from the collapse of massive gas clouds in the early universe. These so-called direct collapse black holes would begin life already large, bypassing the slow early stages. Another possibility involves sustained periods of rapid accretion. In the dense, chaotic environments of the early universe, black holes may have had access to abundant material, allowing them to grow near the theoretical maximum rate for extended periods. Mergers also play a role. Young galaxies collided and combined more frequently in the past. When galaxies merge, their central black holes eventually do the same, adding mass quickly. None of these mechanisms alone fully solves the puzzle. Together, however, they begin to ease it. What is striking is how this process unfolded. The discovery of early quasars did not lead to a crisis. It led to refinement. Models were expanded. Assumptions were revisited. Simulations grew more sophisticated. The universe, once again, didn't need to change. Our understanding did. There is also something subtly instructive about the nature of the evidence. Astronomers did not observe these black holes directly. They inferred their presence from motion, brightness, and physical limits. The black holes themselves remained invisible. Their influence, however, was unmistakable. This pattern mirrors earlier discoveries. Dark matter, rogue planets, magnetars. In each case, gravity and energy revealed what light alone could not. Quasars are particularly elegant examples of this principle. They transform the darkest objects imaginable into some of the brightest beacons in the cosmos. They show that black holes are not merely endpoints, but active participants in galactic evolution. And importantly, they show that the early universe was far more efficient than once assumed. Stars formed quickly, galaxies assembled rapidly, black holes grew with surprising speed. The cosmos did not waste time. This realization reshapes how cosmic history is viewed. The early universe was not a slow, tentative beginning. It was a dynamic, crowded place, full of gas, collisions, and intense activity. From that perspective, the existence of massive early black holes becomes less shocking, though no less impressive. Even so, the tension has not vanished entirely. Questions remain about how common these rapid growth pathways were, and how they interacted with their host galaxies. Some quasars seem too massive even for optimistic models. That uncertainty is honest. It reflects the limits of current observation rather than a lack of effort. There's also a quiet symmetry at play. earlier, galaxies appeared to be missing mass they were expected to have. Here, black holes appear to possess mass far sooner than expected. Absence and excess, both challenging intuition in different ways. What ties them together is gravity. It governs motion, it shapes structure, and under extreme conditions it allows the universe to produce outcomes that feel surprising without being inconsistent. Quasars shining from the distant past remind astronomers that cosmic timelines are not gentle suggestions. They are boundaries to be tested. From here, attention turns once more to age. If some objects grew too quickly, others appear to have existed for too long. Stars whose measured ages seem to stretch uncomfortably close to the age of the galaxy itself. Once again, the universe presents a puzzle not of impossibility, but of precision. And once again, careful measurement will decide where understanding must adjust. The resolution did not arrive as a revelation. It arrived quietly, through precision. As distance measurements improved and stellar models became more refined, the most extreme age estimates began to settle. Stars once thought to be older than the galaxy were still ancient, but no longer contradictory. They fit within a coherent timeline, one where the Milky Way formed gradually, assembling itself over long stretches of time rather than appearing all at once. These stars were not older than the galaxy. They were older than the galaxy in its present form. Many of them formed before the familiar disk existed, during an early phase when the Milky Way was still gathering material through mergers and accretion. Their elongated orbits and sparse chemical makeup reflect that origin. They are relics of a formative era, preserved not because they resisted change, but because they were born early enough to witness it. What once appeared to be a paradox turned out to be a reminder of how sensitive cosmic measurements can be. Small uncertainties in distance, composition, or internal stellar physics were enough to stretch timelines beyond comfort. When those uncertainties were reduced, the universe returned to consistency without needing revision. These stars remain extraordinary, not because they broke chronology, but because they anchor it. They mark the earliest stages of galactic history, offering direct insight into conditions that existed long before the Sun formed. Their value lies in what they confirm, not in what they seem to threaten. Age, however, is only one way the universe records its past. Motion tells another story. Stars trace individual paths, but galaxies move as populations, responding to gravitational influences on scales far larger than any single system. And when those motions were measured carefully, patterns began to emerge that pointed not to time, but to direction. Galaxies are not still. They drift through space, carried along by the expansion of the universe, each one slowly moving away from the others as space itself stretches. This overall motion is smooth and predictable. Measure the distance to a galaxy. Measure how fast it's receding, and the two line up neatly. That relationship has been confirmed again and again. But layered on top of that smooth expansion is something subtler. Individual galaxies do not simply ride the cosmic flow. They also move in response to nearby mass. They fall toward clusters. They orbit common centers of gravity. They are tugged and redirected by structures large enough to bend space itself. This additional motion is known as peculiar velocity. Not peculiar in the sense of strange, but peculiar in the sense of belonging to the galaxy alone, separate from the general expansion of the universe. For decades, astronomers have measured these deviations carefully. Most are modest. A cluster pulls in its neighbours. A filament channels motion along its length. The patterns usually make sense once the surrounding mass is accounted for. Then, in the latter half of the 20th century, something unexpected emerged. When astronomers mapped the motions of galaxies in the local universe, many of them appeared to be drifting in the same general direction, not randomly, not locally, but coherently. across an enormous volume of space. They were flowing toward a region of sky in the direction of the constellation Norma. At first, this seemed implausible. The region lay close to the plane of the Milky Way, where dust, gas, and stars obscure much of what lies beyond. This zone, often called the zone of avoidance, makes direct observation difficult. Optical telescopes struggle to see through it. Even infrared surveys face challenges. If something massive was hiding there, it was well concealed. Yet the motion was unmistakable. Galaxies tens of millions of light-years apart showed velocities that could not be explained by local structures alone. They were being pulled, slowly, steadily, but persistently. This pull became known as the Great Attractor. The name suggests a single object, something monolithic and mysterious, exerting its influence from behind the galactic curtain. In reality, the situation is more nuanced. The Great Attractor is not one thing. It is a region of space containing an enormous concentration of mass, clusters of galaxies, superclusters, dark matter woven through it all. Together they create a gravitational basin deep enough to influence the motion of galaxies across vast distances. What makes this discovery remarkable is how it was made. No image revealed it. No bright signal announced its presence. It was inferred entirely from motion, from careful measurements of how galaxies deviated from expected expansion. Gravity, once again, revealed what light could not. To quantify this effect, astronomers compared the observed velocities of galaxies with what would be expected from expansion alone. The difference pointed consistently in the same direction. The farther out the measurements extended, the clearer the pattern became. This was not a local anomaly. It was large-scale structure announcing itself through dynamics. As surveys improved, parts of the obscured region were gradually revealed. Radio and infrared observations began to uncover dense clusters of galaxies hidden behind the Milky Way's dust. One of the most significant was the Norma cluster, a massive assembly of galaxies contributing substantially to the gravitational pull. Even so, the story did not simplify into a single culprit. The Great Attractor is better understood as a convergence point within the cosmic web, where multiple structures overlap and reinforce one another. It is a reminder that gravity does not care about visibility. It accumulates wherever mass gathers, luminous or not. There is a quiet elegance to this. The universe leaves signatures of its structure in motion itself. Even when direct observation fails, dynamics remain readable. This discovery also reinforced an important idea. Large-scale structure matters locally. The Milky Way is not isolated. It is part of a vast network of galaxies responding to gravitational influences extending far beyond immediate neighbours. Our own galaxy, along with the local group, is moving as part of this flow. The sky itself carries a subtle imprint of this motion, visible in the way ancient background radiation appears slightly warmer in one direction and cooler in the opposite. Nothing here is dramatic. The speeds involved are small compared to the speed of light. The timescales are enormous, yet the coherence of the motion is undeniable. There is also something slightly unsettling about it. To know that entire regions of the universe are drifting towards something that cannot be fully seen challenges intuition. It forces a reliance on inference rather than image, on trust in measurement rather than visual confirmation. And yet, this is not speculation. The equations of motion balance, the data converges, the gravitational accounting closes. The Great Attractor does not threaten understanding, it strengthens it. It confirms that gravity operates consistently across scales. That mass, even when hidden, leaves measurable fingerprints, and that the cosmic web is not an abstract concept, but a dynamic framework shaping the motion of galaxies themselves. Over time, the mystery has softened. As more of the obscured region has been mapped, the attractor has become less singular and more structural. less a secret object, more a natural outcome of how matter clusters in the universe. But it remains a powerful example of how discovery can proceed without sight. First came motion, then inference. Only later did partial images follow. There is a lesson here that echoes through many areas of astronomy. Not everything announces itself with light. Some things reveal themselves only through their effects on others. This perspective becomes increasingly important as attention shifts inward. If galaxies can be influenced by unseen mass across millions of light years, then much closer to home, the solar system may not be as isolated as it appears. Objects can arrive from beyond its boundaries, wanderers shaped elsewhere passing briefly through familiar space, not pulled by hidden clusters, but carried by their own long histories through the galaxy. Sometimes, the most interesting discoveries are not the things that stay put, but the ones that pass through. The solar system is often imagined as a closed neighborhood. Planets follow stable paths, comets return on predictable schedules, asteroids trace familiar routes shaped by the sun's gravity. For centuries, this picture held up well. Everything seemed to belong here, bound to the sun since the system's formation. That sense of isolation did not survive careful measurement. Modern sky surveys do not simply look for beauty, they look for motion. Night after night, the same patches of sky are imaged and compared. Anything that shifts position stands out immediately. Software flags it. Astronomers take a closer look. Most moving objects are easy to classify. Asteroids orbit the sun. Comets arrive from distant reservoirs but still remain gravitationally tied to the solar system. Their paths curve smoothly, tracing elongated but familiar shapes. Then, not long ago, something appeared that didn't fit. It was faint, small, moving quickly. At first, it looked like another minor body passing through the inner solar system. But when its trajectory was calculated, the numbers refused to cooperate. Instead of following a closed loop around the sun, its path was open. A clean, decisive curve that entered the solar system, swung past the sun once, and headed back out into interstellar space. This was not a visitor returning someday. It was a passerby. The key clue lay in the shape of its trajectory. Objects bound to the sun follow elliptical paths. Even long-period comets remain gravitationally tethered. This object followed a hyperbolic trajectory, meaning it had too much speed to be captured. Its motion could not be explained by anything native to the solar system. It had come from elsewhere. This was the first confirmed detection of an interstellar object passing through the solar system. Not a theory, not a simulation. An actual body formed around another star, drifting through the galaxy long before briefly crossing our path. The discovery itself was almost anticlimactic. No flash, no warning. By the time its nature was recognized, it was already on its way out. There was no opportunity to plan a close encounter, no chance to send a spacecraft. Astronomers had to make do with what little time remained. That limitation shaped everything that followed. Observations were hurried but careful. Telescopes around the world were turned toward the object. Its brightness was measured, its color analyzed, its motion tracked as precisely as possible before it faded beyond detection. What emerged was a portrait full of uncertainty. The object did not behave quite like a typical comet. It showed little obvious gas emission. Its brightness varied in ways that suggested an unusual shape, possibly elongated or flattened. Its acceleration did not match expectations based solely on gravity. Each of these features sparked discussion, and in some cases confusion. But it's important to separate what was observed from what was inferred. What was observed was motion, a hyperbolic path, a clear interstellar origin, variations in brightness consistent with rotation, a small but measurable non-gravitational acceleration. What was inferred depended on models and assumptions. Outgassing of volatile materials, surface properties, shape, composition. Each interpretation carried uncertainty, amplified by the brevity of the encounter. This was not a failure of astronomy, it was a reminder of its limits. An interstellar visitor offers no second chances. Miss the window, and the object is gone, possibly forever. There is no orbit to wait for, no predictable return. That scarcity of data is precisely what made the discovery so compelling. It demonstrated beyond doubt that the solar system is not sealed off. Objects move between stars. Planetary systems exchange debris. The galaxy is not a collection of isolated islands, but a dynamic environment where material migrates over immense timescales. Since that first detection, additional candidates have been identified, reinforcing the conclusion that interstellar visitors are not exceptionally rare. They are simply difficult to catch. Estimates suggest that at any given moment, one or more such objects may be passing through the inner solar system unnoticed. Most are small, most are faint. Without continuous monitoring, they slip through undetected. Detection capabilities are improving. Surveys now scan larger areas of sky more frequently, increasing the chances of early identification. With more warning, future visitors may be studied in greater detail. Even so, some questions may remain out of reach. What exactly are these objects made of? How long did they drift through interstellar space before encountering the Sun? What processes shape them in their original systems? How representative are they of material formed around other stars? With only brief observations, answers remain tentative. There is also something quietly humbling about the timescales involved. These objects may have wandered the galaxy for millions or billions of years before passing through our neighborhood. Entire civilizations could rise and fall during such a journey. And yet, the encounter itself lasts only months. From the object's perspective, the solar system is just a brief detour. This discovery subtly changes perspective. The solar system is not just a place of origin. It is also a crossroads. Material formed elsewhere can arrive unannounced, carrying physical records of environments far beyond our reach. No dramatic conclusions are required. No speculation about intent or purpose. The significance lies in confirmation. The galaxy is permeable. Stars form planets. Planets scatter debris. Some of that debris escapes. Over time it drifts, guided only by gravity, until it encounters another star. Occasionally that star is ours. There is a certain quiet poetry in this. The Sun, like countless others, is both host and passerby in a much larger system. The boundaries drawn on diagrams are conveniences, not barriers. Motion reveals this truth more clearly than light ever could. And motion, when measured with enough precision, also reveals something else. That time itself does not behave uniformly everywhere. That near massive objects, even something as fundamental as the flow of time, can shift, slow, and diverge in measurable ways. The story of movement through space naturally leads there, because the path of an object is shaped not only by where it goes, but by how time unfolds along the way. Time feels steady. Seconds pass at a familiar pace. Clocks tick reliably. Days unfold in a sequence that seems universal and shared. For most purposes, time behaves as though it is the same everywhere, moving forward at a single agreed-upon rate. Physics does not agree. More precisely, physics agrees only approximately, and only when gravity is weak and speeds are modest. Step outside those conditions and time begins to reveal a quieter, stranger truth. Time does not flow equally everywhere. This idea was once deeply unsettling. It challenged common sense in a way few scientific ideas ever have. How could time itself change speed? How could two identical clocks disagree, not because one was broken, but because reality demanded it? For a long time, this remained theoretical. Elegant mathematics suggested the effect, but theory alone is not enough. Astronomy and science more broadly demands measurement. That measurement eventually arrived. Gravitational time dilation describes a simple but counterintuitive fact. The stronger the gravity, the more slowly time passes. Not metaphorically, not perceptually, literally. A clock placed deep in a gravitational field ticks more slowly than an identical clock placed farther away. This is not an illusion. It is not a trick of observation. It is a physical difference in the passage of time itself. The reason lies in how gravity shapes space and time together. Massive objects curve the fabric of space-time around them. Motion through that curved space-time changes how time unfolds. Near a massive object, the path through space-time is steeper. Time stretches. This may sound abstract, but the effect is measurable, and it has been measured. The first clear confirmations came from experiments involving precise atomic clocks. These clocks are so accurate that they can detect differences in time passing at different heights above Earth's surface. A clock placed on a mountain ticks slightly faster than one at sea level, because it experiences slightly weaker gravity. The difference is tiny, amounting to billionths of a second over long periods, but it is real, repeatable, and predicted exactly by theory. Satellites make the effect even clearer. Global positioning systems rely on clocks aboard satellites orbiting Earth. These clocks experience weaker gravity than clocks on the ground, and they move at high speeds relative to Earth's surface. Both factors affect time. If these effects were ignored, positioning errors would accumulate rapidly, rendering the system useless within hours. Instead, the corrections are built in. Every day, technology quietly confirms that time does not flow uniformly. These measurements are not limited to Earth. Astronomy extends them far beyond. Near dense objects such as neutron stars and black holes, gravitational time dilation becomes dramatic. In these environments, gravity is so strong that time slows significantly, relative to distant observers. While placing a clock near a black hole is not currently practical, nature provides alternatives. One involves observing light emitted from material orbiting compact objects. The frequency of that light shifts in predictable ways as it climbs out of deep gravitational wells. These shifts match the expectations of time dilation precisely. Another involves binary systems, where a compact object orbits a companion star. By tracking orbital motion, pulse timing, and spectral changes, astronomers can measure how time behaves under extreme conditions. One of the most striking examples comes from pulsars, rapidly spinning neutron stars that emit beams of radiation with extraordinary regularity. These beams sweep across Earth like clock hands, allowing astronomers to measure their timing with astonishing precision. When pulsars orbit massive companions, their pulses arrive slightly early or late depending on their position in the gravitational field. The pattern reveals how time slows and speeds up as gravity changes. Once again, theory meets observation. Time dilation is not speculative. It is not philosophical, it is empirical. There is a certain calm in that fact. The universe is not behaving oddly. It is behaving exactly as it must once gravity and motion are accounted for properly. What feels strange is not the effect, but the assumption that time should be absolute in the first place. From this perspective, time dilation becomes less mysterious and more inevitable. It also introduces a quiet hierarchy. There is no universal now, no single cosmic clock that governs everything. Each object carries its own proper time, shaped by where it is and how it moves. This does not lead to paradox in practice. Differences are usually small. Only under extreme conditions do they grow large enough to matter in obvious ways. But those extreme conditions exist. Near the event horizon of a black hole, time dilation becomes so pronounced that, from a distant perspective, processes appear to slow dramatically. Matter seems to freeze as it approaches the boundary, its signals stretched thinner and thinner. From the matter's own perspective, however, time flows normally. Both descriptions are correct. This duality is not a contradiction. It is a feature of how time works. Astronomy has learned to live with this quietly. Time dilation is folded into models, calculations and interpretations. It is no longer a surprise, it is a tool, and yet it remains unsettling in a gentle way. It reminds us that even the most familiar aspects of reality depend on context. That time, like distance and motion, is not fixed, but relational. That the universe does not offer a single, shared rhythm. There is also a practical consequence. Extreme environments allow effects that are negligible elsewhere to become dominant. In these regions, time dilation is not a curiosity. It shapes observable behavior. It influences how matter accretes, how radiation escapes, how signals propagate. It leaves fingerprints in light itself. Which brings the focus naturally to brightness. Because when time changes, so does energy. And when energy shifts under extreme conditions, light can behave in ways that challenge intuition just as deeply as time once did. In some regions of the universe, light flickers faster than expected. It varies on timescales that seem incompatible with the size of the objects producing it. And once again, careful measurement shows that nothing is broken. It is simply that the universe is operating where familiar assumptions no longer apply. Light is usually patient. Stars brighten and fade over years. Galaxies evolve over millions of years. Even violent events viewed from a great distance tend to unfold slowly. When astronomers watch the sky, they expect change to arrive gradually, softened by scale and time. Quasars did not follow that expectation. Quasars are powered by supermassive black holes, surrounded by vast disks of gas spiraling inward under gravity. As material falls closer to the black hole, it heats to extreme temperatures, releasing enormous amounts of energy. This process turns the central region of a galaxy into one of the brightest objects in the universe. For a long time the picture seemed clear: large object, large energy output, large timescales. Then astronomers began to notice something unsettling. Some quasars changed brightness far too quickly. Not over years, not over months, sometimes over days, in a few cases over hours. The light would brighten, dim, and brighten again with a speed that did not seem to match the size of the system producing it. This posed a very specific problem. There is a fundamental connection between how fast something can change and how large it is. Information cannot travel faster than light. If an object brightens as a whole, that change must propagate across the emitting region. A very large region cannot coordinate itself instantaneously. In plain terms, fast flickering implies a small source. But quasars were known to be enormous. This contradiction was not subtle. The brightness changes were measured repeatedly, by different observatories, at different wavelengths. The data did not drift. It remained consistent. Once again, the discomfort lay not in the measurements, but in what they implied. If the entire quasar were brightening and dimming that quickly, it would violate basic physical limits. So something had to give. Either the understanding of quasars was incomplete, or the variability was being misinterpreted. Astronomers chose the cautious option. They assumed the models needed refinement. The first step was to examine what part of a quasar was actually changing. While the overall structure is enormous, not all of it contributes equally to the observed light. Much of the energy comes from the innermost regions of the accretion disk, close to the black hole, where gravity is strongest and temperatures are highest. Those regions are far smaller. This helped, but it did not solve everything. Even the inner disk seemed too large to vary so rapidly, at least under earlier assumptions. The brightness changes still appeared uncomfortably fast. Attention then turned to relativistic effects. Near a black hole, motion approaches the speed of light. Time dilation becomes significant. Light is beamed and focused by motion and gravity. Small regions can dominate the observed signal. In such environments, intuition built from everyday experience becomes unreliable. Models were updated to include turbulence in the accretion disk, hotspots orbiting close to the black hole, and magnetic processes capable of releasing energy in bursts rather than smoothly. Instead of imagining the quasar as a steady glow, astronomers began to see it as a dynamic, restless system. This shift made a difference. Rapid variability no longer required the entire quasar to change at once. It could arise from localized regions, flaring briefly, then fading, while the larger structure remained stable. The overall energy budget still balanced. The laws of physics remained intact. But the discomfort did not disappear entirely. Some quasars still seemed exceptionally efficient at turning in falling matter into light. They appeared to emit more energy than expected given the amount of material involved. This placed them firmly in the category of objects that emit more energy than they seem like they should. The resolution again lay in details. Energy extraction near a spinning black hole can be extraordinarily effective. Magnetic fields can tap into rotational energy. Relativistic effects can amplify observed brightness. Geometry matters. Orientation matters. What looks excessive from one angle may be perfectly reasonable from another. As these factors were incorporated, the extreme cases became less extreme. Not ordinary, but understandable. There is an important pattern here. The universe didn't present a single clean puzzle. It presented overlapping constraints: speed, size, energy, gravity. Each had to be satisfied simultaneously. Only when models accounted for all of them together did coherence return. This process took time, years of observation, decades of theoretical work, gradual refinement rather than sudden insight. And through it all, the quasars kept flickering. There is something almost comforting in that persistence. Nature does not pause while understanding catches up. It continues doing what it does best, leaving humans to reconcile their expectations afterward. Quasars, once thought of as simple beacons, emerged as some of the most complex systems known. Their brightness variations became tools rather than problems. By studying how quickly and how intensely they change, astronomers can probe conditions that would otherwise be inaccessible. Variability reveals size, it constrains structure, it exposes the influence of gravity and motion at their extremes. In this sense, rapid flickering is not an inconvenience. It is information. It tells a story about matter pushed to its limits, about energy released under conditions where small regions dominate large outcomes, about light-carrying signatures of environments far beyond direct reach. There is also a quiet symmetry at work. Earlier, the universe presented objects that formed too quickly, or appeared too massive too soon. Here, it presents objects that change too quickly, or shine too intensely for comfort. In each case, the resolution does not lie in abandoning physics, but in applying it more completely. What remains striking is how often these discoveries depend on patience rather than spectacle. Quasar variability is not dramatic in a cinematic sense. It is detected through careful monitoring, statistical analysis, and long-term attention. No single observation settles the matter. Patterns emerge only with time, and time, as it turns out, is always part of the story. As understanding of rapid brightness changes has matured, the sense of contradiction has faded. Quasars are no longer seen as violating physical limits. They are seen as inhabiting regimes where those limits become visible. They remind astronomers that extreme does not mean impossible. It means informative. From brightness that changes too quickly focus shifts towards something quieter. Because the universe is not only surprising in what it shows, but also in what it withholds. In some cases, expectation builds, probability suggests abundance, and yet observation returns silence, not flickering, not glowing, just absence. And in astronomy, silence can be just as revealing as light. Silence is not usually treated as a discovery. In science, attention gravitates towards signals, toward things that flash, move, emit, or change. Absence feels passive by comparison, easy to overlook or dismiss, and yet in astronomy, silence can be deeply informative, especially when there are strong reasons to expect noise. That expectation began to build in the 20th century as understanding of stars and planets expanded rapidly. The Milky Way contains hundreds of billions of stars. Many of them are similar to the Sun. Observations now show that planets are common, not rare. Most stars host planetary systems. Many of those systems include rocky planets. Some reside in regions where liquid water could exist on a planet's surface. These facts alone reshape perspective. If planets are abundant, and if the basic ingredients for chemistry are widespread, then the conditions that led to life on Earth might not be exceptional. Add to this the immense age of the galaxy, measured in billions of years, and it becomes reasonable to imagine that technological civilizations could arise elsewhere, perhaps long before humans existed. From this line of reasoning, a quiet expectation formed, not of visitors, not of contact, but of evidence, signals, artifacts, traces, something somewhere detectable across interstellar distances, and yet nothing obvious has appeared. No unambiguous transmissions, no engineered structures visible from afar, no unmistakable signs of widespread technological activity. This mismatch between expectation and observation is often referred to as the Fermi paradox. Though it is not truly a paradox in the logical sense, it is an observational tension, a question framed by incomplete data rather than contradiction. The tension begins with numbers. Even conservative estimates suggest that the galaxy should host vast numbers of potentially habitable worlds. Stars have been forming for over 10 billion years. Civilizations, if they arise at all, might persist for thousands, millions, or even longer spans of time. Over such durations, even slow expansion or communication could leave detectable footprints. The absence of those footprints invites scrutiny. But before drawing conclusions, it is essential to examine the assumptions beneath the expectation. Detection is not trivial. Searching for extraterrestrial signals relies on choices. Which frequencies to monitor, which directions to observe, how long to listen, what qualifies as artificial rather than natural. Each choice narrows the search dramatically. The universe is not quiet in absolute terms. It is filled with natural radio emissions, background noise, and transient events. Distinguishing a deliberate signal from this background requires precision and patience. Even then, signals may not resemble what humans expect. Communication methods could be brief, narrow, intermittent, or entirely unlike radio transmission. Civilizations may not broadcast continuously. They may not broadcast at all. There is also the matter of time. Human radio leakage has been detectable for barely over a century, a blink on cosmic timescales. If technological phases are short relative to stellar lifetimes, then overlap between civilizations could be rare, even if life itself is common. Two civilizations separated by a few thousand years might miss each other entirely. Distance compounds this challenge. Signals weaken with range. Artifacts become harder to resolve. Even ambitious surveys cover only tiny fractions of the galaxy at any given time. Search efforts have been real and sustained, but they are still limited. Projects scanning the sky for artificial signals have examined only a small portion of possible frequencies and locations. It is not that nothing has been found everywhere. It is that very little of everywhere has been checked. Silence, under these conditions, does not carry a single meaning. It does not imply that life is rare. It does not imply that intelligence is impossible. It does not imply that humanity is alone. It implies that current searches have not yet intersected with a detectable signal. That distinction matters. Astronomy is full of examples where absence preceded discovery by decades. Pulsars went unnoticed until instrumentation improved. Fast radio bursts hid in data archives for years. Rogue planets escaped detection until indirect methods matured. In each case, the universe was not withholding information. Observers simply lacked the tools or perspective to recognize it. There is also a deeper layer to consider. Technological civilizations may not leave obvious traces. They may prioritize efficiency over broadcast. They may exist in forms that do not produce large-scale energy signatures. They may alter their environment subtly, in ways that blend into natural processes. Human expectations are shaped by human history, but the universe is under no obligation to follow that template. There is a gentle irony here. Earlier discoveries revealed objects that emitted too much energy, flickered too quickly, or formed too rapidly. Here the surprise is the opposite. A lack of excess, a lack of noise, a restraint that feels almost deliberate, though there is no evidence that it is. Silence invites projection, which is why restraint is essential. The most scientifically grounded position is not despair or certainty, but patience. The Fermi tension does not demand an answer yet. It demands better data. New instruments are expanding search capabilities. Larger surveys scan broader regions of sky. Improved signal processing can identify subtler patterns. The range of possible technosignatures under consideration has widened beyond simple radio transmissions. Even so, results will accumulate slowly. This is not a field where breakthroughs arrive daily. It is one where null results matter, but only in aggregate. Each quiet observation narrows possibilities slightly, refining understanding rather than closing doors. It's also worth noting that silence itself has shaped perspective in a constructive way. It has encouraged humility. It has discouraged assumptions of centrality. It has reminded scientists that expectation must remain tethered to evidence, especially when dealing with probabilities stretched across astronomical scales. The absence of detection does not diminish the richness of the universe. If anything, it underscores how much remains uncharted. There is a certain calm in accepting that. The cosmos does not owe confirmation to curiosity. It unfolds on its own terms, offering information when conditions allow, withholding it when they do not. And silence, in this context, is not emptiness. It is a boundary marker showing where observation currently ends. Beyond that boundary, possibilities remain open. What is known with confidence is this: the universe is vast, planets are common, chemistry is universal, time is abundant. These facts stand independent of detection efforts. What remains uncertain is how those ingredients combine elsewhere, and how often they produce outcomes recognizable from afar. For now, the sky listens back with no clear reply. That quiet does not close the story, it pauses it. And as attention shifts from what is heard to the fabric of space itself, a different discovery waits. One that does not involve signals or silence, but the behavior of space on the larger scales. Because even as the universe appears quiet, it is not still, it is expanding. And not just expanding, but doing so in a way that no one expected at the time it was first measured. For much of the 20th century, the expansion of the universe seemed like a settled idea. Galaxies are moving away from one another. Space itself is stretching. The farther a galaxy is, the faster it appears to recede. This relationship was measured, tested, and confirmed repeatedly. The remaining question was not whether the universe was expanding, but how fast it was slowing down. Gravity, after all, pulls inward. Matter attracts matter. An expanding universe filled with galaxies and clusters should gradually lose momentum, its outward motion decelerating over time. That expectation felt reasonable. It fit intuition. It fit the mathematics. And for decades, it framed how cosmologists thought about the future of the cosmos. Then astronomers began measuring something new. They turned their attention to a particular kind of stellar explosion, one that occurs when a white dwarf star reaches a critical mass and detonates. These explosions shine with a remarkably consistent intrinsic brightness. That consistency makes them useful. By comparing how bright they appear with how bright they are known to be, astronomers can determine their distance. These events are known as Type 1a supernovae, and they can be seen across vast stretches of the universe. By the late 1990s, independent teams were using these supernovae to map the expansion history of the cosmos. The goal was straightforward: measure how fast the universe was expanding at different times in the past, and determine how gravity had influenced that expansion. The results were not what anyone expected. Distant supernovae appeared dimmer than they should have been. Not by a small margin, but consistently so. The implication was subtle, but profound. Those supernovae were farther away than predicted. Space had expanded more than expected during the time their light was in transit. This meant that the expansion of the universe was not slowing down, it was speeding up. The first reaction was disbelief. Measurements of this magnitude demand caution. Distances can be misjudged. Dust can obscure light. Supernovae might vary more than assumed. Every possible source of error was examined. The teams compared notes. They checked calibration. They tested alternative explanations. Different instruments, different samples, different methods all pointed to the same conclusion. The universe's expansion is accelerating. This discovery reshaped cosmology almost overnight. What is measured clearly is the effect itself. Distant galaxies are receding faster now than they were in the past. The rate of expansion has increased over time. This conclusion is supported not only by supernova observations, but also by independent measurements involving the cosmic microwave background and the large-scale distribution of galaxies. The evidence converges. Something is causing space to expand faster as time goes on. What that something is remains uncertain. To describe the effect, cosmologists use the term dark energy. This is not a substance in the usual sense. It is a label for whatever is driving the acceleration. It may be a property of space itself. It may relate to vacuum energy. It may reflect a deeper aspect of gravity not yet fully understood. The name is practical, not explanatory. It is important to be precise here. Dark energy is not invoked because scientists lack imagination. It is invoked because measurements require something that behaves in a very specific way. It must act uniformly across space. It must exert a repulsive influence that grows more significant as the universe expands. Whatever it is, it dominates the energy budget of the cosmos. Ordinary matter, the stuff of stars and planets, makes up only a small fraction of the universe's total content. Dark matter accounts for more, shaping structure through gravity. Dark energy outweighs both. This realization carries a quiet weight. The future of the universe is no longer governed primarily by gravity pulling things together, but by expansion pushing them apart. Over time, distant galaxies will recede beyond detectability. The observable universe will become emptier, not because matter disappears, but because it is carried out of view. And yet, for all its consequences, dark energy remains elusive. Astronomers can measure its effects with increasing precision. They can track how expansion has changed over cosmic history. They can test whether the acceleration is constant or evolving. So far, the simplest description fits the data well. But description is not explanation. No experiment has directly detected dark energy as a physical entity. There is no particle to point to, no field that has been isolated conclusively. The universe is accelerating, and the reason why remains open. This is not a failure of science. It is a boundary. Cosmology has reached a point where observation is clear, but interpretation is incomplete. The measurements are robust. The implications are unavoidable. The underlying cause has not yet been identified. There is a certain symmetry here. Earlier discoveries revealed missing mass. Dark matter entered the picture because galaxies moved as if extra gravity were present. Here, something extra is inferred, because space behaves as if an outward influence exists. In both cases, the universe announces its contents through motion rather than light. It is also worth noting what dark energy does not do. It does not tear apart galaxies. It does not disrupt planetary systems. On small scales, gravity and other forces dominate. The acceleration becomes noticeable only across immense distances, where the cumulative effect of expansion outweighs local attraction. This restraint is part of what makes the discovery so striking. The effect is everywhere, yet subtle, powerful, yet patient. The universe is not racing apart violently. It is drifting faster than expected. There is a gentle humour in how this was uncovered. Astronomers set out to measure deceleration and instead discovered acceleration. The universe answered a question that had not been asked. This pattern is familiar by now. Careful observation opens doors that expectation did not anticipate. The discovery of accelerating expansion does not invalidate earlier understanding. It extends it. Gravity still governs structure. Galaxies still form. Clusters still bind. But on the largest scales, another influence sets the pace. What remains unresolved is how this influence fits into a deeper theory of physics, whether it reflects a property of empty space, a modification of gravity, or something else entirely. For now, cosmology lives comfortably with that uncertainty. The universe is expanding faster over time. That statement is measured, tested, and supported by multiple lines of evidence. The explanation is provisional, awaiting further insight. In the meantime, attention turns back to structure, because while expansion governs the large-scale fate of the universe, the arrangement of galaxies, clusters, and filaments is shaped by something else, something invisible yet deeply influential, an unseen form of matter that pulls inward while space itself pushes outward. Understanding how these opposing influences interact is key to understanding why the universe looks the way it does today. And it begins, once more, with something that cannot be seen directly, but whose presence is written clearly into motion. Most of what holds the universe together cannot be seen. Galaxies rotate as if wrapped in invisible halos. Clusters bend light from objects far behind them. Large-scale structure grows in patterns that visible matter alone cannot produce. Across many independent observations, gravity appears stronger than luminous material can account for. This unseen influence is known as dark matter. Its presence is inferred, not imagined. Rotation curves of galaxies flatten where they should fall. Gravitational lensing reveals extra mass along lines of sight, where little light is present. Computer simulations of cosmic structure only reproduce the observed universe when a dominant invisible component is included. Taken together, the evidence is overwhelming, and yet despite decades of effort, dark matter itself has never been directly detected. This absence is not a footnote. It is one of the most persistent and carefully examined results in modern physics. Indirect evidence for dark matter is everywhere. Galaxies behave as if embedded in massive halos. Colliding clusters show separations between luminous gas and gravitational mass. The cosmic microwave background encodes precise information about how matter clustered in the early universe, and those patterns require dark matter to match observation. None of this depends on a single method or assumption. The conclusion emerges repeatedly, across scales ranging from individual galaxies to the entire observable universe. Dark matter, whatever it is, exerts gravity. It interacts with light only through that gravity. It does not shine, absorb, or emit in any detectable way. That very property makes it difficult to catch. Direct detection experiments are designed with a simple goal. If dark matter particles pass through Earth, then on rare occasions they might collide with ordinary matter. Those collisions would deposit tiny amounts of energy, measurable with sufficiently sensitive instruments. To maximize the chances, detectors are built deep underground, shielded from cosmic rays and background radiation. They use ultra-pure materials, cooled and isolated, monitored continuously for faint signals. What these experiments test is not existence, but interaction. They ask whether dark matter particles interact with ordinary matter beyond gravity, and if so, how strongly. So far, the answer has been silence. No unambiguous signal has emerged. No collision rate has risen above background noise. Each new experiment improves sensitivity, probes new parameter ranges, and reports null results. At first glance, this might seem disappointing, but in science, null results are information. Each non-detection rules out entire classes of candidates. It excludes particles above certain interaction strengths. It constrains mass ranges. It narrows theoretical possibilities. The space of what dark matter could be has been shrinking steadily. Early ideas focused on particles that interact weakly, but not negligibly with ordinary matter. These candidates were attractive because they fit neatly into existing theories and offered natural explanations for cosmic abundance. As experiments ruled out large regions of this parameter space, attention shifted. Lighter particles, heavier particles, different interaction mechanisms, entirely different frameworks. The absence of detection has not stalled progress. It has guided it. There is an important distinction here. Dark matter has not failed to appear where it must appear. It has failed to appear where it might have appeared. Gravity alone already confirms its presence. Direct detection seeks additional properties. The universe has not contradicted itself. It has simply declined to reveal further detail so far. There is also the possibility that dark matter interacts so weakly with ordinary matter that detection is extraordinarily difficult, or that it interacts in ways current experiments are not designed to notice, or that it is not a particle in the conventional sense at all. Each of these possibilities remains open, constrained, but not eliminated. This situation is not unique in science. History is full of cases where indirect evidence preceded direct confirmation by decades. Neutrinos were proposed long before they were detected. Gravitational waves were inferred long before instruments could measure them. Patience in these cases was not passive, it was productive. The same applies here. Dark matter detection failures do not weaken the case for dark matter, they sharpen it. They tell scientists where not to look, which ideas no longer fit, and how experimental design must evolve. There is also a philosophical comfort in this restraint. The universe is not obliged to yield all its components easily. Some aspects may remain hidden until tools and concepts mature enough to meet them. In the meantime, dark matter continues to shape the cosmos visibly through invisible means. Galaxies form where dark matter collapses first. Filaments trace its distribution. Clusters assemble around its gravitational wells. Ordinary matter follows the scaffolding laid down by something it cannot see. This invisible architecture defines the universe's large-scale appearance. And yet on smaller scales, dark matter remains elusive. It passes through Earth unnoticed. It drifts through detectors silently. It leaves no tracks except in motion and structure. That duality is striking. Dark matter dominates the universe by mass, yet refuses to reveal itself directly. It governs the largest patterns in existence, yet avoids interaction at the smaller scales. This balance raises deeper questions. Why does dark matter interact gravitationally but not electromagnetically? Why does it clump on cosmic scales but remain diffuse locally? Why does it shape galaxies without participating in chemistry or light? These are not idle curiosities. They point toward fundamental properties of reality. Whatever dark matter is, it occupies a different role than ordinary matter. It obeys gravity, but appears otherwise aloof. It contributes mass, but not complexity. It builds structure, but does not seem to form structures of its own in familiar ways. This separation may be telling. It suggests that the laws governing the universe allow for multiple categories of substance, each with its own behavior and influence. Visible matter is not the default. It is one component among several. The fact that dark matter detection remains incomplete does not signal failure. It signals that understanding is asymmetrical. Gravity has revealed one aspect, other interactions have not. That asymmetry itself becomes a clue. As experiments continue, sensitivity improves. New detection strategies emerge. Astrophysical observations place tighter constraints. Theoretical models adapt. The search remains active, informed by every null result. Dark matter is not hiding out of spite. It is following rules not yet fully known, and in the meantime its existence forces careful thought about balance. Balance between forces, between expansion and attraction, between parameters that allow structure to form without collapsing too quickly or dispersing too rapidly. That balance is not limited to dark matter alone. It extends to the laws of physics themselves, to the values of constants, to the delicate conditions that permit long-lived stars, stable atoms and complex structures. From invisible matter that refuses to appear, attention naturally shifts to the fine margins that govern everything else. Because the universe does not merely exist. It exists within narrow boundaries that allow it to persist, evolve, and become interesting at all. The universe operates on numbers that do not announce themselves. They are not written across the sky or etched into matter in any visible way. They sit quietly beneath everything, shaping how particles interact, how forces behave, and how structures emerge. These numbers are known as physical constants, and without them, the universe would not look anything like it does. A physical constant is simply a value that does not change. It sets the strength of a force, the mass of a particle, or the rate at which processes unfold. Once set, it applies everywhere and everywhen. Atoms rely on these values. Stars rely on them. Galaxies rely on them. Most of the time they fade into the background. Physics uses them routinely, plugging them into equations, building predictions that work with remarkable precision. It is only when scientists ask a particular kind of question that the constants draw attention to themselves. What would happen if they were different? This question is not philosophical by default. It is practical. Physics allows certain values and forbids others. By exploring how sensitive physical systems are to these values, scientists can test how robust the universe really is. The results are striking. Small changes in some constants lead to large consequences. Alter the strength of the electromagnetic interaction slightly, and atoms may not hold together. Change the balance between nuclear forces, and stars may fail to shine for long enough to produce heavier elements. Adjust the mass of certain particles, and chemistry as we know it may never arise. This sensitivity is what is often referred to as fine-tuning. The term can be misleading. It does not imply intention. It does not imply design. It simply describes how narrowly constrained certain values appear to be if a universe with long-lived structure is to exist. Consider stars. Stars are powered by nuclear fusion, a process that depends delicately on the balance between forces inside atomic nuclei. If the strong nuclear force was slightly weaker, protons would struggle to bind. Fusion would stall. Stars might never ignite. If it was slightly stronger, fusion could proceed too rapidly, causing stars to burn out quickly or collapse into unstable configurations. Either way, the result would be a universe very different from the one observed. The same sensitivity appears in chemistry. Atoms form because electrons remain bound to nuclei at stable distances. This depends on a precise relationship between electric charge, particle mass, and quantum behavior. Modify those relationships modestly, and atoms either fall apart or collapse inward. Complex molecules become impossible. The chemistry required for planets, atmospheres, and biology never emerges. Gravity adds another layer. If gravity were much stronger, stars would collapse quickly, burning hot and short. If much weaker, gas clouds might never collapse at all, leaving the universe filled with diffuse material but no stars. The observed balance allows stars to form, shine steadily, and seed space with heavier elements over billions of years. These examples are not cherry-picked. They emerge repeatedly when physicists explore alternative parameter values within known laws. The conclusion is not that the universe is uniquely perfect, but that it occupies a narrow region of possibility space where complexity can arise. This is an observational statement. It is also important to clarify what science can and cannot say here. Science can state with confidence that certain physical constants fall within ranges that permit stable atoms, long-lived stars, and structured galaxies. It can demonstrate that moving outside those ranges leads to universes that are simpler, shorter-lived, or radically different. Science cannot currently explain why the constants have the values they do. That gap is real, but it is not an invitation to fill it prematurely. There are several ideas under investigation. Some theories suggest that constants are not fundamental at all, but emerge from deeper laws. Others propose that many sets of constants may exist across a wider reality, with observers naturally finding themselves in regions compatible with observation. These ideas remain speculative, constrained by mathematics and consistency rather than direct evidence. What matters here is restraint. Fine-tuning does not require metaphysical conclusions. It does not demand answers beyond physics. It simply highlights sensitivity. The universe appears to sit near boundaries where small changes matter. This perspective carries a quiet humility. It reminds scientists that explanation and description are not the same thing. The ability to calculate outcomes does not guarantee insight into origins. Some questions remain open, not because they are forbidden, but because available tools have not yet reached them. There is also a subtle inversion at work. Earlier the universe presented missing matter, unseen but influential. Then it revealed accelerating expansion, driven by something unknown. Now it presents constants that appear delicately balanced. In each case, observation is clear, interpretation lags behind. This pattern does not weaken confidence in science, it reflects its honesty. Boundaries are marked explicitly, claims are tied to data, unknowns remain labelled as such. There is a certain calm in this approach. Fine-tuning, when treated carefully, does not inspire alarm. It inspires curiosity. It raises questions about deeper structure, about whether current theories are complete, and about what might lie beneath the surface of familiar laws. It also reinforces an important point. The universe is not arbitrary. Its behavior follows rules. Those rules are consistent across space and time. They allow prediction, stability, and continuity. The fact that those rules occupy a narrow range of possibility is not a flaw. It is a property to be understood. Complexity, it turns out, is fragile. It requires conditions that are neither too extreme nor too permissive. Too much force, and structures collapse. Too little, and nothing binds. The universe balances between these extremes with remarkable precision. This does not mean it is rare, it means it is specific. From a scientific perspective, specificity invites explanation, not speculation. It encourages deeper theories that might one day show why these values could not have been otherwise, or why variation itself is part of a larger framework. Until then, fine-tuning remains an observational fact with open interpretation, and there is no urgency to resolve it prematurely. The universe functions, stars shine, galaxies form, time flows, matter interacts, life, at least in one corner, emerges. Understanding how all of that rests on narrow margins adds depth, not anxiety. It encourages appreciation for how interdependent physical laws truly are, how changing one aspect ripples through everything else, how stability emerges not from excess, but from balance. As the exploration draws toward its close, this sensitivity serves as a unifying thread. From fleeting signals to ancient stars, from invisible mass to accelerating space, the universe consistently reveals itself through tension between expectation and observation. Not through contradiction, but through precision. What remains is not a single mystery to solve, but a landscape of interconnected phenomena, each constrained, each informative, each pointing toward a reality that is coherent, even when it resists full explanation. That coherence, held together by narrow margins and patient laws, is perhaps the most remarkable feature of all. The universe has never promised to be simple. It follows rules, but it does not arrange them for comfort. It behaves consistently, but not always in ways that feel intuitive from a human point of view. When observed carefully, it reveals patterns that hold across vast distances and deep time, alongside details that resist easy summary. That combination is not a flaw, it is a feature. Throughout this exploration, the same theme has surfaced in different forms. Signals that arrive too briefly to feel plausible, yet repeat often enough to demand attention. Stars compact enough to crack their own surfaces. Planets wandering without suns. Regions of space so empty that absence itself becomes a structure. Ancient light carrying faint irregularities from the universe's earliest moments. Galaxies behaving as if much of their mass is missing. Black holes growing faster than expected. Stars whose ages brush against the earliest history of the Milky Way. Whole populations of galaxies drifting toward mass that cannot be seen directly. Objects passing through the solar system from beyond it, never to return. Time itself flowing at different rates depending on gravity and motion. Light changing more quickly than size alone would suggest. Silence where signals might reasonably have been expected. Space expanding faster over time, driven by something still unnamed. Invisible matter shaping everything while refusing to show itself. Physical constants resting within narrow margins that permit complexity at all. None of these observations contradict one another. They coexist. That coexistence is important. The universe is not a collection of isolated puzzles. It is a single system operating across many scales. What appears strange in one context often becomes necessary in another. What feels excessive here balances something subtle elsewhere. What remains unexplained does not imply disorder, only that description has advanced faster than interpretation. Science at its best is comfortable with that imbalance. Description is not failure, it is foundation. Before explanations can be trusted, reality must be mapped carefully and honestly. Measurements must be repeated. Patterns must persist. Outliers must be tested rather than dismissed. Many of the discoveries discussed here spent years, sometimes decades, in that uncomfortable space between detection and understanding. And yet, in each case, coherence held. Fast radio bursts did not rewrite physics. They revealed environments where physics operates at extremes. Magnetars did not defy matter. They showed what matter becomes under immense pressure and magnetism. Rogue planets did not undermine planetary formation. They revealed its dynamism. Cosmic voids did not suggest chaos. They completed the picture of structure. The cold spot did not erase the early universe's uniformity. It highlighted its subtle variation. Even where explanation remains incomplete, consistency remains intact. Dark matter has not been seen directly, but its gravitational influence fits seamlessly into cosmic history. Accelerating expansion has no agreed cause, but its effects align across independent measurements. Fine-tuning raises questions, but those questions arise precisely because the laws of physics behave reliably enough to explore hypothetical change. The universe does not hide its behavior. It simply does not summarize itself. There is a quiet humility in recognizing this. Not every observation must lead immediately to an answer. Not every tension demands resolution within a single generation. Some exist to mark the edges of understanding rather than to collapse them. This does not diminish progress. It defines it. Over the last century, astronomy has moved from speculation to measurement with remarkable speed. Instruments now detect signals lasting thousandths of a second from across the observable universe. They measure motions of galaxies hidden behind dust. They track time differences smaller than a blink across Earth's surface. They infer structure from absence and mass from motion. None of this required the universe to become simpler. It required patience. There is also something reassuring in how often intuition fails gently rather than catastrophically. Expectations are nudged, not shattered. Models stretch, not snap. Each discovery adds texture rather than contradiction. The universe does not behave randomly. It behaves lawfully, even when those laws produce outcomes that feel surprising. Perhaps that is the central lesson. Reality does not owe clarity to the observer. It owes only consistency to itself. The role of science is not to demand simplicity, but to recognize structure where it exists, to describe faithfully what is measured, and to remain honest about what remains uncertain. In that sense, mystery is not a deficiency, it is an indicator of depth. There is no requirement that all questions be answerable within a single framework, or even within a single era. Some phenomena may wait for new tools, others may wait for new ideas, a few may remain open longer than comfort allows. That openness is not weakness, it is restraint. The universe continues to expand. Matter continues to cluster. Time continues to flow unevenly. Light continues to carry information across unimaginable distances. Objects pass through and move on. Structures form and dissolve. Constants hold steady. Everything observed so far points to a cosmos that is not fragile, not arbitrary, and not designed for easy explanation. It is simply real. And that reality, described carefully rather than oversimplified, carries its own quiet wonder. Not the wonder of spectacle, but the wonder of coherence across scale, of laws that apply equally to atoms and galaxies, of patterns that emerge without instruction, of complexity balanced on narrow margins without apparent effort. There is no final conclusion to draw from this, no single answer to offer. Only an invitation to notice, to observe without rushing to resolve, to accept that understanding grows incrementally, to allow strangeness to coexist with reliability. The universe does not owe simplicity, it offers consistency instead. And within that consistency there is more than enough to hold attention, invite curiosity and reward patience, long after the questions themselves have settled into quiet orbit. The universe does not resolve itself neatly. It reveals patterns, then stretches them. It confirms expectations, then gently exceeds them. What appears strange rarely breaks the rules. It simply operates where intuition thins out. Across vast distances and deep time, reality remains consistent, even when it refuses to feel simple. Description comes first, explanation follows when it can. For now, it is enough to observe clearly, measure carefully, and accept that some truths arrive fully formed, while others take longer to settle. The universe continues on its way, indifferent to comfort, steady in its laws, and quietly more intricate than any single story can contain.